On this channel, we provide useful programming information with practical code examples. This time, we will cover WebGL in TypeScript. We will introduce the concept of WebGL, its minimal configuration, rendering, extensions, and class design step by step with sample code. Enabling subtitles will make the code descriptions easier to understand. WebGL is a low-level API that allows you to manipulate the GPU directly in the browser. By using TypeScript, you can greatly reduce implementation mistakes in WebGL through type safety, code completion, and structured coding. TypeScript is especially effective in the following points. The types of WebGL objects become clear. Mistakes in handling shader variables can be reduced. It becomes easier to track the structure. The following are the minimum requirements for rendering with WebGL. Less than canvas, greater than element. WebGL context. Vertex shader. Fragment shader. First, let's create a state where the screen can be initialized. First, obtain the canvas and WebGL rendering context. Here, we use TypeScript coding with an emphasis on null safety. At this point, GL becomes the entry point for all WebGL operations. Before rendering, check whether the background color can be filled. This is the initial check to verify that WebGL is functioning correctly. Up to this point, the canvas will be filled with a dark gray color. In WebGL, drawing processes are described using a special language called GLSL. In GLSL, you mainly prepare two types of shaders: vertex shaders and fragment shaders. First, we will create a minimal working shader using these two shaders. Vertex shaders determine the positions of points or figures to be drawn. The following is simple code that places a single point at the center of the screen. A position is the coordinate passed from the JavaScript side. Fragment shaders determine the colors that appear on the screen. This time, it always outputs red. Precision must always be specified in WebGL. Since shader creation processing is always the same, we turn it into a function. This function creates a shader of the specified type, compiles the source code, throws an error if it fails, and returns the compiled shader if successful. Combine the vertex and fragment shaders into one. This is called a WebGL program. This code links the vertex and fragment shaders into a single program and checks if they can be used for rendering. Here, we will prepare vertex data for drawing a triangle. The coordinate system in WebGL ranges from -1.0 to 1.0. Next, to make the array of vertex data usable by the GPU, we transfer the data using a buffer. This code creates a buffer to store vertex data and transfers its contents to the GPU. Connect a position in the shader with the buffer previously created. Finally, use the program to issue the rendering command. When you run this program, a red triangle will be displayed. WebGL is an imperative API, so the code can rapidly become bloated if written as is. Through class design, you can clearly separate initialization, rendering, and resource management. Here, we will leverage the advantages of TypeScript and progressively evolve the design to focus on separation of concerns, reusability, and maintainability. The class is divided into the following roles. GL app controls overall initialization and rendering. Shader program manages the shaders. Triangle mesh manages the vertex data. First, let's create the class that controls everything. GL app manages the canvas and WebGL context and serves as the starting point for rendering. This class manages the initialization and rendering processes of WebGL and is responsible for drawing to the screen using shaders and meshes. By separating initialize and render, it is easier to support re-initialization and animation in the future. Next, create a class to manage shaders, consolidating shader creation, linking, and usage into one place. This allows the rendering side to focus only on using them. This class unifies the creation, linking, and usage of vertex and fragment shaders, enabling the rendering side to use shaders safely. By exposing getAttrib location, it can be safely referenced from the mesh side. We will also create a class to manage the vertex data. By dividing mesh classes by object to draw, it becomes easy to extend. This class manages the vertex data of the triangle and, by linking it to the shader, handles the actual rendering. All the information needed for rendering is contained within triangle mesh. Finally, combine the classes to launch the app. With this structure, adding animations or multiple meshes becomes easy. Using TypeScript with WebGL offers the following advantages. By converting WebGL procedures into classes, they can be organized by role, making maintenance and extension easier. By separating responsibilities such as rendering and shader management, code readability is improved. By utilizing TypeScript's type completion, you can reduce mistakes in calling WebGL APIs or specifying parameters. By using TypeScript, even low-level WebGL processes can be stably handled with type safety and structure. By understanding the flow from minimal configuration to rendering, and by applying class design to separate roles such as initialization, rendering, and resource management, you can improve readability and maintainability. By implementing step-by-step, you can learn WebGL as practical knowledge that is not a black box and can be applied in real work. The source code for this video can be downloaded from the official website. If you like, please visit the URL in the description to aid your learning. Thank you for watching. If you'd like to enjoy more content, please subscribe to the channel.